Okay, thank you to be here for the lecture of today. I would like answer the question about how many parameters can be considered is in terms of augmentation, and then in order to realize an eccentric gamma filter. Do you remember last time we have seen the observer for a desiccator in which we measured voltage in input, and we measured the voltage of the capacitor as a state of the system, and we estimated current, voltage of the capacitor, resistance, and capacitance. Now, question is, may augment a little bit more and to estimate also inductance? Or in general, how many augmentation I can do for a given measurement? We have seen also in your case, we estimate one parameter, no? And the question is, how many parameters in this Lotka-Volterra equation to recognize fakes, or in general COVID structure is this possible without losing the observability? About the observability, I already told you. Let me repeat a little bit two things from the first lecture, or the first presentation. It's not exactly the first lecture, but the first PDF document you can find in my study. As I told you, I hope that starting from tomorrow, I will upload the lectures in the YouTube channel. Everything is free. And then I will realize in a folder with all manuscripts. Because of the augmentation, we have seen that the system becomes a nonlinear system, at least in its model is a nonlinear system. Not necessarily each augmentation generates a nonlinear system, but in our case, yes. And as I told you, the augmentation is always a problem because we add, or at least the augmentation which I presented, the augmentation realized using a Gaussian variable is always a problem because we didn't put deterministic knowledge. We put something which is stochastic. This means characterized by the distribution, Gaussian distribution, and this means in any case by the mean value, by the variance, and so on. We have seen for the observability in the context of a linear system that we had this result, this test, which is a theorem, which is necessary and sufficient condition. We can see that the observability depends on the matrix C, which is the map of the sensor, depends on the matrix A, which is the map of the dynamics of the system. I don't know if you remember. In any case, depends just of output and the structure of the system. Similar consideration can be done for a linear system. I forgot to say it is in a linear time invariant system. Similar consideration can be done for a linear system, even though time variant. This is time invariant, and this is time variant. Both conditions, this is a rank condition, state a necessary and sufficient condition. Now, what happens in case of a nonlinear system? It doesn't matter if the nonlinear system is a physical nonlinear system or is our representation nonlinear. This means the augmentation generate a nonlinear representation, which can be used in the eccentric gamma filter. Nevertheless, nonlinear the representation. Look, we have in the literature 4 concepts of the nonlinearity of the observability in nonlinear systems: locally observable, locally weak observable. A little bit more complex, even though we have basically in general just one test, this one, just for the locally weak observable. I will tell you exactly this today. But just a few words about this four possible definition. We can see that the strong definition is the locally observability, which implies all the rest. Locally observable is in a system this is observable. You remember about the observability I told you at the beginning of the course. Just moving around our equilibrium point, about the nonlinear system, we speak about equilibrium points, in generally local, no? Around the working point, more in general, just moving a little bit. If I am able to identify, to observe, to distinguish, to remember the concept of the distinguishability, I did it emphasize with math, with mathematical issues or mathematical insights, but I told you, if this is enough, this is the strongest concept because imply the locally weak observable, imply the observable, and we imply the weak observable. Now, let me start from the observability. If it's locally observable, means that it's observable also in large, because it's enough to move a little bit around the equilibrium points or around the working point. Could be also a trajectory. This means this observability in large is guaranteed if the system is observable in a local situation. Why is also this implies also the local weak observability? Because weak means, in the sense that I need the input to observe the system in locally weak observable. This means that the system is a little bit lazy. I need to apply an input to be able to distinguish between two states, between two things which I want to estimate. It's clear that in this case here is more conservative because I need an input. Weak is related to the necessity to have an input, to stimulate the system. In this sense, the observability in linear sense is not weak, it's strong, because we don't need the input. To remember, the test does not depend on the matrix B. Now it's clear that this concept here, the weak observable, is implied by all the rest because if the system is also locally weak observable, is also weak because this means in large, with input in large. Here this without input in large. Okay, look at the test and then we will do some example using MATLAB. Easy example in order to understand. I don't want to consider the example last time because it's complicated. I will consider another example a little bit, probably a little bit more, I would like to say easier, yeah. Look, we have here a nonlinear system, the general nonlinear system, which we can see that the nonlinearity could be also in the output. Could be also in the output. About that, I will tell you. We say that the system is observable if the rank is in the linear case of this structure here, which is not what we have seen in linear cases. Yeah, in both cases, invariant and variant. The rank is n. Look now together about A0, A1, A2 until On, this structure here. But before going ahead, look that the theorem is just an if condition. This means just a sufficient condition. We lose the necessity in nonlinear case. This is typical in when we pass from linear to nonlinear. Why is this typical? Because the necessity says to us when a system, in this case, is not, let me say, observable. In this sense, the sufficient is more conservative, of course. Nevertheless, say when is observable, but if the condition, this rank condition is not satisfied, we cannot conclude anything. And this is a typical situation passing from linear and non-linear structure in which condition preserve the sufficient, but not preserve the necessity. Let me look at O0, O1, O2, and so on. Look, it seems a little bit complicated. I will show you an example, and we will see extremely easy. And MATLAB will help us. I will tell you together with MATLAB. In any case, just flesh out this observability matrix. We can see that the first element is the gradient of age output with respect to x. Transposed just formally. If you don't like, you don't consider transposed. Basically, it's the gradient. I don't know if you remember what the gradient is. Basically, is a vector. Characterized, or the component of the vector are the partial derivative of the state of the system. No, because x is our state, which consists. Do you remember last time we have seen current, voltage, R, and C. 4 states. X consists of 4 states. This means if we apply this method to the system of last time, we have here a row with 4 components. The derivative with respect of age, respect to current, the derivative of age, respect to UC, and so on. What about the second element? If you look here, this gradient here is exactly O0. What is this expression here? Is O0 scalar f, even though it's not written, but I tell you, scalar f means, if you look here, f is the field. This means in a vector. It's in a vertical vector, let me say, in a column vector, to be precise. O is in a row vector. This means O0 scalar f is in a scalar function. And then we do the derivative, or better to say, this gradient, which consists of the partial derivative of this scalar function with respect to the state vector. And then this is recursive again, because also from here to here, I am using the result which we have here. From here to here, I will use the result which I have here, because this element here, everything, this row which appear here, is called O1. This row is the vector, row vector, which I called O1. And then I apply here again. Okay, let me show an example. At the beginning, some calculation by hands. And then I will switch on MATLAB, because typically these calculations, for this calculation, we use MATLAB, because it could be that we can make mistakes. But just to show you a little bit more in depth what we do, I have here some slide or manuscripts to show you. Don't do it. It's vegan. It's vegan. You do. Show me this. One second. I don't have better than this. It does not matter. Let me switch on the lateral camera. Yeah. Look, again, the system. It's in the general system. Now, and it's expressed the system in the general form. Now, let me show you a concrete case. Just to repeat, the system which we have seen here in equations 1 is observable if exists. Please pay attention, just if. No? And a determinant O, observable interaction, not 0. Why A? Very important. At this moment, I did emphasize this A, 1. Because we have, depending on how many measurements I have in the output, we have, as in state out, as how many states I measure, depending how many states I measure, we have let me say, a lot of determinant to be checked. The reason is, I show you now, even though I don't have I have an example, I think. Not in MATLAB, but I have an example to show you. The matrix which we have as an observability matrix is in a full column rank matrix. It's just in a square matrix if we have just one output measurements. In this course, we will consider just one output, but in practical application, we have more than one output measure. Output measurements, I intend state which I measure. Of course, if I measure more, it's easier to observe because you have more possibility also mathematically. If I have just one state which I measure, we have just one determinant to check. This reflects the concept that if I measure more and more states, if I have more and more information, it's clear it's easy to build an observer, also to observe the system because I have more information. This is reflected in this concept. This I already told you. And then look at this example. Look at this example. We can see that we have a system with 3 states, but 2 of them, I would like to say, are artificial state or augmented state. We called here correctly augmented state. But artificial in the sense, it's not correct to say artificial, but I would like to say without artificial in the sense, you remember I told you the derivative of R equals 0, the derivative of L equals 0, cover just deterministically, cover just the case in which R and L are constant. In the sense, I would like to use the word artificial, but of course, we don't have the model means. This means is a strong assumption that the derivative of the variable is 0. But in the context of Kalman, we say that they are variable, Gaussian variable. This means can change. Remember, this I told you a lot about. The system is this one. Question is the system observable? Second question, if I will consider just the system here, is more or less observable? Even though I don't tell you about the measurement of the observability, but we will see that we can understand when we show you with MATLAB that if I consider this augmentation with just one parameter, the system is more observable because I don't need many conditions to be satisfied in order to obtain the determinant not 0. But intuitively, we can understand because I would like to identify less elements. I mean, I don't care about L. With the same, of course, with the same measurement. Given some measurements, if I include more parameters to be estimated, I lose the level of observability. And it happens that it could happen that the system is not more observable, even though we cannot prove because the condition is sufficient. But if the condition is not satisfied, of course, we suspect that it's not observable. Look at some calculations. Why O0 is 100? And then I will show you with MATLAB. Why O0 is 100? It's 100 because here I assume to measure the current. I don't know if I told you here. Yeah. H is a linear function. In this case, could be also nonlinear. In this case, it's linear. It's the current, right? This means the Jacobian of this H with respect of the state as vector x, state vector is characterized by current, resistance, and L. Is 1, 0, 0, because the derivative of the current with respect to the current is 1, the derivative of the current with respect to the R is 0, the derivative of the current with respect to L is 0. Therefore, this is the vector, the gradient O0. Then I have to do O0 scalar F. Sometimes we didn't put this dot here. No? O0 scalar F means 1, 0, 0, which is O0, scalar this vector. Why that? Because this vector is the field F. First component, second component, and third component of what? Of my system f of x, comma u, x derivative equal f of x, comma u, x derivative f of x, comma u. Here, this x derivative is this component as a vector, this component, this component, this component. Once we do the product, which basically get just this element here, we have our O scalar f. Now, O1 is the gradient of O scalar f. Basically, I have to do these calculations. And you have this element, and this element. Why that? Because the derivative of this scalar with respect to I is minus R divided L. The derivative of this scalar with respect to R is I divided L. Why that? Because R appears linearly just here. Clear, no? Derivative. Now, the derivative of this scalar with respect to L, we have an L in the denominator. Here is a little bit more complicated because we have to recall the rule of the derivative. You remember, 1 divided x. What is the derivative of 1 divided x? Is minus 1 divided x squared. If you don't remember, it does not matter because I will tell you how we can do now with MATLAB. Because in this case, we can do by hands. But if this is complicated as last time, but also this is not so easy. If you go ahead, yeah, I did this calculation. It's not so, this is O2, no? If you go ahead, if you do O2, you can see that it could happen that we make mistakes. I mean, until here, it's not so extremely difficult, but this component, we have to remember what is the derivative when the variable is in the denominator. Then you have this expression. And then you have to do this scalar f again, and it's a little bit more complicated. And then look, could be difficult. Let me show you with MATLAB, because I am interested to show MATLAB how we can verify the observability. And then I will compare, as I told you at the beginning, with MATLAB, this case with this case. Once with just a parameter, and then with two parameters. And we will see, even I didn't define any measurements of the observability, that the case in which I want to estimate just R is easy to be achieved in terms of parameter, in terms of conditions, which must be satisfied to attain this. Again, if this condition is not satisfied, we cannot say anything because the theorem is just an sufficient condition. Okay, let me open MATLAB. I need 1 second. Because this, of course, is slow, the system, but where is MATLAB? Let me show you. Let me share in the meantime MATLAB. let me I I think I have to share again. Yeah. Now, look what I have here. I will upload also this. No? Test of the observability for the following system. Exactly what I told you. Of course, we assume if L is not zero, this I forgot to say, but it's clear, because otherwise I cannot divide by zero. Not only therefore, if L equals zero, the system is not a dynamical system. It's no problem, not really, but we don't need Kalman in the sense. And we have the state, augmented state R, and the augmented state L. Look what we have here. I express more concretely what I told you about the number of measurements in output, no? State, measured state. Moreover, I put also here more in depth the concept of the how many determinants I have. Look, I can demonstrate, I don't have time, that the number of the determinants to be checked is this one. This means N is the number of the states. In our case, 3. P is the number of state which I measure. I told you output measurements. No, then to be precise, the state measurement, but in the sense it's an output. Multiply by the state. It's not visible, but I will show you. P is the number of measured state multiplied by the state itself, the number of state itself. Excuse me, it's a little bit too small. Now, could be visible. Of course, it's just one, the determinant to be checked, in case the measured state is 1. It is written also here. Because in this case, this calculation is 1. One variable. We can see here. This factorial is clear what is, no? From math. N factorial is clear what is. If the state equals 3, is 3 multiply 2 multiply 1, 6. Factorial. I think in German is Fakultät. Fakultät. Factorial in English, factorial. Factorial product. If n is 4, means 4 multiply 3, multiply 2, multiply 1. 1 you can forget. You know? In some books, you multiply by 0, but 0 factorial is 1. Is definition. I don't want to in depth on this, but why this statistical concept? This also reflects a little bit that if I measure more than one state, statistically, we have more possibility because basically the information is passing through a more complicated network, and this is easy to obtain an observer. And not only, we can also in this context consider the measurements of the observability. Also, the determinant is the measurement of observability. Let me show you. Did you agree? This SIMS indicates the symbolic variable. Sim means symbolic. S, I don't know, probably is plural, I don't know what. But in any case, I, R, L, U, the T is a little bit in an artificial form I don't remember if I used, to indicate the derivative of the current with respect to the T. Anyway, everything or every element which appear after this command here are considered as yeah, symbolic variable. Symbolic means we will consider the command I show you as symbolic, as we write in the in paper. I show you. It's not numerical, not 1, 2, 3. It's like an algebra. No? Look here. F is our field. You can see here's a vector characterized by 3 components. You remember, I told you this. What is this line here? Is this? F. This element, this element, this element. It's a vector of this element, this element, this vector. F is a vector. Victoria, it's difficult. It's difficult. Eh? I try to simplify as I can. I try to simplify as I can. Sena, it's difficult. You have seen a little bit. Hmm. Should I repeat a little bit, Victoria? Because you don't remember the from math, or you didn't have math. Okay, this is more difficult because if just something which I don't remember, it could be that I can recall, or you can slowly you can recover this information or this knowledge or this concept. You can say as you want. But let me go ahead. As I told you, depending on your background, I will give you the task that makes sense. Otherwise, we have to do a complementary just for engineer, complementary just for data science, and complementary data science is not, I'm not here, right or no? Okay, now we have to go ahead a little bit. Look, O0 we calculate easily, but I can calculate also symbolically how I can do as I did for O1. O1, I used the symbolic because it was not immediate. Do you remember? Let me show you what. This diff state the partial derivative of this scalar function with respect to this variable. Why this is a scalar function? Because it's a scalar product between this vector and this. Let me be a little bit more precise. This row vector and this column vector. At the end is in scalar. Which one? F. This means this element here will be my gradient. I will show you. This is the same, but represent the gradient. Excuse me, make mistakes. This element here is the first component of the gradient. Excuse me, a little bit. The first component of the gradient, because it's the first partial derivative of this scalar function. This is the second component of the gradient. This is the third component of the gradient. The gradient is this. Yeah, the gradient of O0 scalar F1. the gradient of the scalar function O0 scalar 1. Now, once we understood this, but it's not many things to understand, just to remember what I'm doing now, what I explain now, because we avoid all these boring calculations, the derivative. Then we do O2 in the same form, just replacing O0 with O1, and then we're ready. For the system consists of three states, current, R, and L, because we have to proceed from O0 until On minus 1, but n is 3, this means until O2. Then I will do the determinant, and I am ready. We will see if the determinant at full rank or not. We have just one determinant to be calculated. Let me show you quickly the case just with R. This is the field. Gradient of the output now is not 1, 0, 0 anymore, but just 1, 0, no? Because we don't have L. We can ignore L. This means I don't care about L, assuming that I know perfectly, in order to understand better. What about O1? Yeah, is S before, but I don't have to consider the derivative with respect to L. This is the gradient of O0 scalar F. Or let me say O1. Ready to build the observability matrix. Now, in this case, the observability matrix consists of just O0 and O1. Why that? Because we have just two states, starting from O0 until On minus 1, means n is 2. We have to stop O1. Then I do the determinant. Let me run. Of course, now, one understood a little bit this technique. It doesn't matter how many states I have. How doesn't matter how complex. We leave MATLAB to do the boring work. We leave MATLAB to do the boring work because how possible to say the derivative will be done by diff, the function diff, which consists of two arguments. The function to be differentiated, comma, and the second argument is the variable. Huh? Okay, let me discuss now the results. I hope it works. I hope it works. Yeah. Look. Here we have O1, F, O1, O2, O0 I didn't put because this is 1, 0, 0. I didn't put here the observability matrix. If you want to do the observability matrix, OF, you digit OF, you show, I can show you the matrix, but it's a little bit large, but it's not the problem. If you digit here OF, you have also, I don't know if I have F1, OF1, or F2. No, we have, I override OF, but it's basically consists of O1 A0, O2 A0, and O2, O1 A0, and O2 A0 again. Anyway, let me discuss the results. This answer here says to us a lot of things. Why that? I put it, this calculation, this blue calculation here. Look, this matrix. Now, I can write I see the mistakes. This expression here I see something wrong, no? I will correct. I think should be up to 3, right? Let me see. This is the results. If I put here in evidence U, I will have U, which is I forgot, which multiply this element here. If I put in evidence U from here, no? Then I can write L up to 4 divided L up to 3. Yeah. Excuse me for the error. Now it's correct, no? Why that? I forgot again this U. No, excuse me. It was okay. Because it's not this the tests, but this one, excuse me. The first test is, yeah, was everything okay? I was too too deep in the file. Yeah, this is the test which we did now, no, with 3 variables, which you want to consider. Excuse me. Now I see. Now everything's correct. Excuse me. Did you agree? I put in evidence U here, and then I write everything in this form, which this blue here is the derivative of the curve with respect to the time. Everything divided by L up to 3. Everything is correct. Excuse me. I made a mistake with the second case. Now, we can see that we have the observability if, but please, if I cannot say if and only if, I cannot say if and only if U is not 0, I have to verify when the determinant is not 0. If U is not 0, and of course L not 0 is clear, no? Because remember I put equation in this form, and not only if L is 0, I don't have a deterministic system. No? And then the derivative with the current with respect to the time, not 0. It's interesting this. This means necessarily, I don't want to say, but if I have an input not 0, if the current is not 0, I obtain the observability. This means very often we put noise in input, excuse me, in the state, or you can put also in input, in order to have the derivative of the current with respect to the time not 0. Because it could happen depending on signals which we have that the current becomes to 0. If the current becomes to 0, no more guarantee on the observability. What happens now in case of two state? No, that's okay. We see here that in case of two state, we don't need U equals 0. This means with two state, it's easy to be controlled because we have the observability also with U equals 0. Of course, we can demonstrate that with U equals 0, the observability reduces, but theoretically, we can see here, we don't need U equals 0. The reason is, I show you in, let me say, a criterion which is a little bit heuristic. But nevertheless, interesting. If I don't want to have information about L, assuming that I know perfectly, I don't need a signal U, because to estimate current and R is not so difficult in this sense, because R is, let me say, multiplied by the current, which I measure. This means it's a little bit a criterion, heuristic criterion, Naik-Burut criterion. I mean, if I know the current, I know what happens in R, assuming that L is known. I don't need L. The reason is R meet R with the product. Do you remember the concept of meeting? No? It's a semiotic concept. The current knows, if I measure the current, what was in R is. Of course, nevertheless, I need, this is not zero, because if this is zero, we have something which is not, let me say, dynamics anymore. If I don't have changes, I cannot estimate. This is another important concept in, let me say, yeah, in identification. Let me look if I forgot to say something. But I don't need, in case I don't want to estimate L, the knowledge of U, because L is given. Let me see what I can add here. This was the second case, no, basically in order to, yeah, was this one. Was this one. And here the calculations is here. Huh? Okay. Okay, I would like to introduce now the topic on next week. For next week, if you bring me the materials, or it could be that I have time to. Next week, we will see something related to the nonlinear system, but I will try to do an example, but the nonlinearity came in one case from the physical system, I show you, and in another case from both, from system and from our augmentation. It's the case of SIR model, this COVID model, this logical equation. We will see for the engineer this example here, which we can see that the friction, the friction is an Coulombian friction. Basically, here we have just nonlinearity, I would like to say, which came directly from the physical system. In this sense, let me say it's easier to be estimate because we don't add. I mean, we can add also Gaussian Gaussian variable. But anyway, the critical case is just when we add Gaussian or elements. If you don't have Gaussian elements, of course, could be difficult, but nevertheless, we have a knowledge about the nonlinearity. And we will see this case, and then we will simulate. Okay, let me conclude here the lecture. Let me close the lecture, but we will remain a little bit because I need to recover at least in this during next week or after next week the lecture of last week, and then we will see in February. I will hold also a couple lectures because I think we have to recover. Anyway, I would like to give you some information about the Kalman a little bit more. Yeah, so probably have 5 minutes. I don't know. Are you tired? No. We can nevertheless start with this example. Okay, let me go ahead some minutes. So next week we can accelerate a little bit. Look at this example. It's a mechanical system, which the derivative of the position is equal to the velocity. The derivative of the velocity is an acceleration, is an force divided the mass. Mass equal 1 is an artificial example, but it's an example which reflects a mechanical system. U is a force. This expression here states a nonlinearity because of V squared, because of SGN, which is basically the friction, the Coulomb friction. This states the reaction of a spring. Yeah, here we have a possible representation of this nonlinearity in terms of x2, no, it's the force. I told you a little bit also once I think about this function here, SGN, sinus, and so on. This function here is represented here. Of course, typically we approximate this SGN function with an hyperbolic tangent, with arcotangent, and so on. You remember 2 divided by arcotangent, such that I will realize a variation between -1 and 1. Why we try to approximate this? Because this function is not continuous function, could generate problem in the derivative. In fact, calculating the Jacobian, you remember in the extended Farmer field, the central calculation, the central point is represented by the Jacobian. The derivative of f1, which is this here, with respect to x1, the derivative of f1, which is x2 with respect to x2, and the second line in the same form, the derivative of f2, which is this long expression, with respect to x1, the derivative of f2, the same long expression with respect to x2. Now we can see here, if 1 and x2, and if 2 is x2 derivative, or if you want, this long expression probably is not very well visible. Calculate it at the corrected point of state x1. We do remember x1 hat and x2 hat. And eventually u. Here we have the recoil. In order to be more precise, the previous, no, as I told you. Now we will see next week. We have just a few minutes. I do the discretization of the first equation. I do the discretization of the second equation. I don't know if you remember the unique discretization of which we did, the Forward-Euler. This is written here. I told you about many times. TS is the sample time. At the end of the calculations, believe me, we will obtain this expression and this expression. This means where this comes from, these two equations. Discretization of the original system, which is in a physical system, which we can image continuous. If you explicit this calculation, you will obtain exactly these two expressions. Now, the last thing. What about the calculation of the Jacobian? And then next week we will implement. Easy. Why this is 1 TS? Because the derivative of this variable, this expression, this scalar variable, with respect to x1 is clearly 1 because it's linear with coefficient 1 here. Why this is TS? Because this element here is basically this long expression, which relative long, which is x1 of k, we can say x1 of k with respect to x2 of k minus 1. This means TS. The derivative of this expression here, which is x1 of k with respect of x2 of k minus 1, is TS. If I do the same calculation here, considering, this is the key point which we'll discuss next week, this SGN equal 1. I mean, I clarify a little bit better. Let me do, first of all, the derivative of x1 with respect to x1. x1 of k minus 1, of course. x2 with respect to x1 k minus 1. This expression here. The derivative with respect to x1 is minus 2 ts, because it's here, no? Minus 2 ts. Now, the last sentence, and then we will come back on this next week. What happens here? Here we have the derivative of x2 of k, this long expression, with respect to x2 of k minus 1. Now, it seems, this is 1, clearly, it is. It seems that I am not considering this expression here in the derivative. I mean, the derivative of this expression here is 2 times x2 of k minus 1, which multiply ts as we multiply this one. But I didn't consider the derivative of this, because if you remember this structure, it's 0 everywhere, the derivative. And here, for x2 equals 0, the derivative is not defined, because the function is not continuous. Of course, this is an approximation, because in the point when we have the change, the Jacobian does not reflect what I wrote here mathematically. But this expression here is just a mathematical representation of the physical system. Do you remember I told you that typically we try to approximate this function which is not continuous with a continuous function, the sigmoid function with a continuous function. Now, of course, if you proceed with this approach, neglecting what happens for x2 equals 0, we have an error. But we will see that this error can be compensated by, do you remember, this Gaussian form, in particular the Gaussian form of P minus, which represented the a priori error covariance matrix, in which the Jacobian plays a role. You remember J, which multiply P0, we multiply J plus Q0. This means I can consider included in this Q0, this variance, somehow the error which I have here. But of course, we have to also consider that this is really something which is artificial, because physically we don't have a change which happens so abruptly when x2, the velocity, is close to 0. I will come back on this. I will show you this example. Alternatively, we can consider arcotangent or hyperbolic tangent, and then, of course, here we have to add another element. But we will see that this is element, I don't know if I have an example, you can do also at home, or could be an interesting project also. This element here does not have a strong influence, because I have an influence just for x2 close to 0 to equal 0. Okay, let me close the lecture. Nevertheless, please remain because I would like to talk about the possibility to recover one lecture at least this week or the next week could be. Let me close. Thank you, nevertheless, for your attention. Please remain. We can discuss a little bit also questions, but also a possible lecture in these days.